Today we're going to talk about waves and their properties. Waves in general are always going to carry energy from one location to another. We have two types of waves, mechanical waves and electromagnetic waves. This chapter we're focusing on mechanical waves. Later we'll focus on electromagnetic waves. The difference between the two is that mechanical waves require a medium. A medium is just matter that a wave travels through. So it can be a solid, a liquid, or a gas that a wave travels through. Mechanical waves need that. They need something to travel through. Electromagnetic waves do not need a medium to travel through. So they can travel through nothingness or through a vacuum. Mechanical waves, there are three types. Transverse waves, those are going to be when my medium, or whatever the wave is traveling through, ends up moving up and down, when the direction of my wave is either in this direction or it could be in this direction in this picture. Longitudinal waves are going to move side to side. So imagine that this is a slinky and I've taken some of those coils and pinched them together and then I let them go. When I let them go, I'm going to have areas where the coils are closer together. We call that a compression. And areas where they're farther apart. We call that a rarefaction. Specific types of longitudinal waves are P waves or primary waves that are produced by earthquakes, and sound, which we'll talk about later in the unit. The other type of mechanical wave that I have is a surface wave. So these are going to be the types that occur at a surface, or when I have two or more mediums, which are called media, then I have a surface wave that occurs between those two media or at that surface. So my waves have different properties, and we're usually going to look at transverse waves for these properties because it's easier to draw them and to visualize them using transverse waves, but all waves have these properties. The first property is the time it takes for one cycle of the wave. For my transverse waves, a cycle is going to be when I start at the rest position, that's this black line, go up to a crest, that's the highest point of a wave, and I come down to a trough, which is the lowest part of the wave, and then I come back to the rest position. That would be one cycle. However long that takes is considered the wave's period. Frequency is kind of related to period in that you count how many cycles there are in 1 second. So this wave is labeled as 1 second long. So for this green wave, I have 1, 2 cycles. So the frequency of that wave would be 2, and the unit we use for frequency is hertz. We represent that with capital HZ. So my green wave would have a frequency of 2 hertz, and my blue wave, if I count those, I'd count 1, 2, 3, etc., and I would see that there are 8 cycles of that wave. So the frequency of my blue wave is 8 hertz. To go back to the period then, if this is 1 second, and I was able to fit 2 cycles of the green wave in 1 second, that means that this would be half of a second, and this would be half of a second. So however long it takes for 1 cycle, in this case for the green wave, is 0.5 seconds. For my blue wave, same idea. I would have 1/8 of a second, because if I have 8 of those all together, that would equal 1 second, which is my total length of time. So for one wave, it'd be 1/8 of a second on that blue wave. Wavelength is measured from crest to crest or trough to trough. Those are the easiest ways to measure wavelength. You could also measure it from the beginning of the cycle to the end of the cycle. Any of those measurements should equal the same distance. So I see on my blue wave, I've labeled wavelength as crest to crest, but it could also be trough to trough. Wavelength is represented with a Greek symbol called lambda, and that's what it looks like right there. So if we see that later, that's what we use to represent wavelength. Amplitude is the distance from the rest position, so the black line, to either a crest or a trough. So this is labeled in my picture here. So from the rest position to this crest would be the amplitude of that wave. I could also measure it over here. For my blue wave, it would be from the rest position maybe to this crest. So I can compare their wavelengths, so tiny wavelength, larger wavelength. I can compare their amplitudes, small amplitude, large amplitude. I can compare their frequencies. So if I have 2 cycles versus 8, then obviously the blue wave has a higher frequency. Something to notice about frequency and wavelength is that if I had my green wave, for example, and instead of it being 2 hertz, let's say that I wanted it to be 4 hertz. Well, I need to draw the wave on this same line. So to get 4 cycles, I'd have to squish them together. If I squish them together, then the distance from crest to crest or trough to trough is going to decrease because I've had to push them together. So frequency and wavelength have an inverse relationship, because if I want to increase the frequency, then I have to decrease the wavelength. One more thing. Amplitude is going to tell us how much energy is in the wave. So my green wave has much more energy than my blue wave does. And I know that because of the amplitude, not because of the wavelength or the frequency or the period. The energy in the wave is related to the amplitude.